Hey everybody, as you can tell by the title of this video, I want to explain why we compare the p-value to alpha. And that sounds like it might be a simple explanation, but it turns out it's not. So let's get into the screens and see what we can see here. So I want to start out by talking about a lot about alpha and what it means. So alpha is the probability of a type 1 error or incorrectly rejecting the null hypothesis, or false positive if you prefer that term. Now, this must mean that to commit a type 1 error, we must have the null hypothesis actually be true. If it was false, it would not be incorrect to reject it. It would be correct, right? So the null hypothesis has to be true for us to commit a type 1 error. And specifically, it has to be true, and then we think it's not. So we must calculate alpha, so let me back up one sentence there. Alpha is a probability, right? It's a probability of making a type 1 error. Therefore, in our common conception of probability as area, it is some area shaded in on the null distribution. Because the null distribution is the one that assumes that the null hypothesis is true. To commit a type 1 error, we must have the null hypothesis actually be true. So the null distribution must be the correct sampling distribution to use in this case. And alpha, however big or small we make it, usually 5%, but however big or small we make it, must be some area on that distribution. All right, so that's what alpha is. So why do we just get to choose it, right? I've said many times that we're just going to decide alpha is 5%, which we are. So when I say we, what I mean is the researcher, right? The person doing the research gets to decide what alpha is. It's not a thing you calculate, it's a thing you choose. And the reason that's the case is that as the researcher, we get to decide how unusual a sample would have to be to make us want to reject the null hypothesis. And I just realized my portrait is in front of part of the title here. Sorry, it's a little hard to hide this thing. I'll put myself way down here. So why do we get to choose alpha to be whatever we want? So as the researcher, we are deciding, well, how often to be fooled, essentially. And when I say how often, what I mean is we're deciding what percentage of the samples are going to cause us to reject the null hypothesis incorrectly if we see them. And the null hypothesis is actually true, of course. So the thing you want to see is that alpha is sort of our decision about the circumstances under which we will reject the null hypothesis. So if we set alpha to be 5%, we're saying the most extreme 5% of samples are going to cause me to reject the null hypothesis, even if that's the wrong thing to do, right? Even if that's an error, that's still what we're going to do. And a thing to remember here is when you're rejecting the null hypothesis or not rejecting it, you don't actually know if your decision is correct or not. And there's no way for you to know because all the information you have is your sample, right? And you're going to do whatever the data in your sample tells you to do, right? And if the data says we should reject the null hypothesis, then you will. And it could be the case that you just got a weird sample, right? That's just the thing that happens sometimes, which I'll talk about in another screen or two here. So if we get to choose alpha to be whatever we want, why not 0%? That seems like a better idea, right? Never make a type 1 error. There's a problem with that, though, of course. Otherwise, we would do it, which is that we are working with incomplete information. No matter how big a sample we take, unless it's the whole population, there's going to be some possibility that we get a weird one. So for instance, let's say my population distribution, or excuse me, that my sampling distribution looks like this, or no, sorry again, this is the population distribution. So my population distribution looks like this, and our sample is just by random chance happens to be all these dots. Are we going to think that the mean is here? No. All our data is over here. We're going to think the mean's like way over here. And you might say to yourself, well, like how likely is that? And the answer is not very likely, right? But it is possible. So we can't set alpha to 0 because we are always working with incomplete information. And therefore, it is always possible that we get a weird sample and are fooled. Setting alpha to some tolerable level is our way of dealing with this, right? We're setting a number up front that says, I am only going to be fooled into rejecting the null hypothesis incorrectly this percentage of the time. And we can set it as low as we want, as long as it's bigger than 0. We can make it 99.99% if you want. The problem with that, if you make alpha really, really, really big, really, really, really small, I said 99.99%, I meant 0.001%. If you make alpha really, really small, it will be extremely hard to reject the null hypothesis, because to reject the null, your p-value has to get under alpha, right? So the smaller you set alpha, the harder it is to reject the null hypothesis, and the more extreme your sample has to be. You might say, well, that sounds all right. Like, why wouldn't I want a small probability of making an error? It's because it's a small probability of making a type 1 error. But alpha and beta have an inverse relationship. So if you are very, very reluctant to reject the null hypothesis, which is what setting a very small alpha means, that means that you're going to make a lot more type 2 errors, right? Where you fail to reject the null hypothesis even when you should. So setting an alpha really, really tiny is equivalent to being really, really cautious about rejecting the null hypothesis. And if you're too cautious, there will be times when you should have rejected it and you didn't. And if you make alpha really, 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 really tiny, you will do that a lot. That'll cause you to make a ton of type 2 errors, which are in their own way just as bad as type 1 errors. It's just that we don't usually deal with them. Maybe I'll elaborate on that a little bit later. Yeah, so it is theoretically, or it is technically possible to never commit a type 1 error. And that is, but the only way that's the case is if you are never willing to reject the null hypothesis, that you are unwilling under any circumstances to reject the null hypothesis. You won't make any type 1 errors. Great. You'll make type 2 errors nonstop. So that's not so good. And that's why we set alpha at a small, but a tolerable but small level, right? We try not to make too many type 1 errors, and we try to balance that by also not making too many type 2 errors. Now, I will say this. There's a default of 5%, and there's no good reason for that. Like that's not some magical percentage that minimizes the probability of making type 1 and type 2 error. It's just sort of a generally agreed upon thing. There are lots of statisticians who feel that most alphas should be set, or that alpha should be set based on what sort of thing you're doing, the severity of a type 1 error versus type 2 error, the implied distributions of both type 1 and type 2 errors. And by the way, we are absolutely not getting into the distributions for type 2 errors, too complicated. But like there's a very strong feeling among statisticians that using 5% all the time is not great, because it's not appropriate some of the time. Sometimes it should be 10%, sometimes it should be 1% or 0.5%. And just depends on the relative severity of type 1 and type 2 errors, basically. So I've probably mentioned this about 1 billion times, but most people don't understand statistics, right? And so if you understand statistics, I've used this as an excuse to say you should be willing to help other people who don't understand statistics by writing your conclusions in plain English, by helping them interpret things that they see that are not making sense to them, but do make sense to you. And among the people who don't understand statistics are a lot of researchers. Depending on what you're doing research in, physics or medicine or chemistry or whatever, there's a good chance that that's what you're an expert in and not statistics, right? most people who do actual statistical research don't have like this, or actual research in some area like social science or medicine, don't have some deep understanding of statistics. And so they're probably in all honesty, not capable of making an informed choice about what alpha is. So it's nice to have a default. The problem is that we always use the default. And that's not great. So anyway, that's why 5%, it's just sort of an agreed upon thing that's convenient, works okay. It works okay in most circumstances. It's rare that we really need to change it, but it should probably be movable depending upon circumstances. So anyway, we can't set it to 0% because we're working with incomplete information and therefore cannot be 100% certain that we're not rejecting the null hypothesis incorrectly unless we never reject the null hypothesis, which is bad. So now I want to talk about the title of this video. Why do we compare the p-value to alpha? And so the first thing I want to mention here is, how are those two things the same, right? They sound very different, right? The probability of seeing an observation, assuming the null hypothesis is true, versus the probability of making a type 1 error do not obviously sound like the same sort of thing. Turns out they are, though. So I want to recall what the definition of a p-value is. So here it is, big bold thing on the screen. P-value of an observation is the probability of obtaining that observation, or one that is at least as extreme, assuming that the null hypothesis is true. So we start with that assumption of the null hypothesis being true, which is why we use the null distribution to calculate the p-value. And as we saw a couple of screens ago, we also use the null distribution to calculate alpha. Additionally, both alpha and the p-value are probabilities. So they are both some sort of shaded region on the null distribution. Now, why do we specifically want to compare those two things? Right, because there's other probabilities on that region too. The way to think of a p-value is that it's a measure of how extreme our sample is if the null hypothesis is true, with a smaller p-value meaning more extreme, because the p-value is the proportion of all the samples that are more extreme than the one we actually got. Another way to say that is that if you subtract from 100%, the p-value is the percentile of extremeness. So a p-value of 3%, right, of 0.03 here is more extreme than 97% of all samples because it is in the 1 minus 0.03 or 0.97 percentile, right? It's in the 97th percentile of extremeness of all possible samples. Well, if alpha is 5%, right, and we're saying that we're willing to be fooled by the 5% most extreme samples, and we get a p-value of 3%, then we're saying that that's one of the 5% most extreme samples. So we're going to reject the null hypothesis if we get a p-value of 0.03, assuming we've set our alpha to 5%. So that's why we compare the two things. So I have a picture for you. Is there a helpful diagram? I thought you'd never ask. So here is my null distribution. And for purposes of what we're doing here, since we're talking about alpha, we're assuming that the null hypothesis is actually true, right? And so this distribution is correct. It is the right sampling distribution, is what I'm trying to say. It's the right sampling distribution. So here's our mu. I'm going to put in alpha, right? So this area here, I'm not going to shade this too densely, you'll see why in a second, is 5%. 2.5% on each side, so 2.5. So, all right, the thing I've shaded in is alpha. Right, I'll make a nice little legend here. And then the other thing I'm going to shade in is my p-value. There's black again. So I'm going to shade my p-value pink. So let's say my p-value was 3%, like I said on the last screen. Then that means it is in the 3% most extreme area, right? So it is like here. So as you can see, if my p-value is smaller than alpha, it has a smaller area to fit into. It's not like the p-value falls inside alpha, right? So by saying alpha is 5%, we're saying that these areas are where I am willing to reject the null hypothesis, even though the null hypothesis might be true in that case, right? If I get one of the samples from those regions of the sampling distribution. And the way we measure how extreme a sample is, right, is by the pink area, is by how big our p-value is. And the smaller the p-value, the more we want to reject the null hypothesis. And if the p-value fits inside the alpha area, then we want to reject the null hypothesis. So that is why we compare our p-value to alpha, as opposed to, say, beta, which is complicated. I don't really want to talk about beta too much because you start talking about infinite families of distributions implied by the null hypothesis being false, and I just don't even want to get into it. But yeah, so this is why we do compare alpha, or the p-value, to alpha instead of to, say, beta or something else. It's because they're actually, alpha and p-value are actually very similar things, right? They're both shaded in regions of the null distribution. Alpha sets the bar for where we will reject the null hypothesis versus where we won't, right? If we fall in the middle here, we have decided that we're not going to reject the null hypothesis if we're in here, right? That's not far away enough from the null hypothesis implied by, excuse me, that's not far enough away from the parameter implied by the null hypothesis for us to want to reject it, right? But anything outside of the black bars is far enough away. And so the way we measure how far away from the parameter we are, which is to say how extreme our sample was, is the p-value. And if the p-value is small, that means it's farther out in the boondocks, right? It's farther away. The parameter was farther away than from our, excuse me, I'm saying this badly. The statistic that we calculated was farther away from the hypothesized parameter than we were willing to accept from our null hypothesis, and therefore we reject it. So there you go. That is why we compare the p-value to alpha. I, for a long time, had this as an extra credit question, and I don't think anybody ever even got close. It is not a simple concept. So there you go. You don't actually need to know this to do any of the problems that we're going to have. I probably should have led with that. Now that I think about it, maybe I'll put that on in the module and just say this video is optional. You don't actually have to watch it if you don't want to. Yeah, none of the questions we have will be dependent on the information here. I just thought you might like to know it. And with that said, I'm going to go ahead and wrap up. So I will see you guys in the next video.